What specific problem does your method aim to solve in portrait image animation and manipulation? And how does your approach of jointly learning depth and appearance provide a solution to this problem?
My method aims to address the limitation of existing portrait image manipulation techniques that primarily focus on generating the RGB appearance of faces without considering depth information. By jointly learning both depth and appearance, our approach ensures that the generated depth maps accurately correspond to the facial images, which is crucial for applications like portrait relighting and depth-based image editing. This correlation allows for more realistic and versatile manipulation of portrait images, enabling tasks such as facial depth estimation and artistic control over image generation. Additionally, our model can be adapted for audio-driven talking head videos, maintaining consistency between the generated RGB images and depth maps during performance. Overall, this joint learning framework enhances the quality and applicability of portrait image animation and manipulation.
How does the proposed method work? Please illustrate the main steps of the algorithm, particularly focusing on the joint distribution modeling of RGB and depth images using diffusion models.
The proposed method utilizes a latent diffusion model to jointly generate RGB images and depth maps by modeling a conditional joint distribution. Initially, a reference image is processed through a reference net to extract identity features, which are then injected into the diffusion model to ensure consistency between the generated appearance and depth. The algorithm operates by encoding both the RGB and depth images into separate latent codes, adding noise independently to each, and then concatenating these noised codes for the denoising process. The denoising network is modified to handle this concatenated input, allowing it to predict the noise for both RGB and depth simultaneously. Finally, the model is trained on a combination of studio-captured images with ground truth depth and in-the-wild videos with estimated depth, enabling it to generalize effectively across various scenarios while maintaining high-quality output.
Can you provide a simple illustrative example demonstrating the inner workings of your algorithm, specifically detailing how the appearance and depth are generated from a given reference image?
Our algorithm operates by utilizing a reference image to jointly generate both the appearance, RGB, and depth of a subject. For instance, given a reference image, R, we first extract identity features using a reference net, which captures intricate details of the target identity. These features are then injected into a latent diffusion model that is conditioned on the reference image, allowing the model to generate a conditional joint distribution, PZ_X_0, Z_D_0, R. During the generation process, we independently encode the appearance and depth into latent codes, adding noise to each separately. Finally, the denoising network processes the concatenated noised latent codes to produce the final RGB image, X, and depth map, D, ensuring that the generated depth aligns with the appearance, thus maintaining visual consistency.
What specific theoretical or practical advantages does your method offer over existing approaches that only focus on image generation without depth information?
Our method offers significant theoretical and practical advantages over existing approaches that focus solely on image generation. Firstly, by jointly learning both appearance and depth, we enable a more accurate representation of facial features, which enhances applications like monocular depth estimation and depth-conditioned portrait editing. This joint learning allows for precise control over the generated RGB images by modifying the corresponding depth maps, leading to photorealistic results that respect the identity of the original images. Additionally, our architecture facilitates post-processing tasks such as portrait relighting, where depth information is utilized to compute surface normals for lighting adjustments, a capability absent in traditional image-only models. Finally, our method extends to audio-driven facial animation, generating synchronized depth maps alongside RGB images, thereby introducing a new dimension of realism and consistency in animated outputs that existing methods lack.
Can you discuss how you validated your method, including the datasets used and the metrics employed to measure your performance in depth estimation and image manipulation tasks?
We validated our method using a combination of datasets, including a high-quality multi-view studio face dataset with 336 subjects and corresponding high-fidelity registered meshes, which provided precise ground truth depth maps. Additionally, we incorporated in-the-wild audiovisual sequences from the HDTF and VFHQ datasets, where we estimated pseudo-ground truth depth maps using a state-of-the-art monocular face tracking approach. For depth estimation, we evaluated our model on an unseen studio dataset consisting of 1264 images, employing metrics such as absolute relative error, ABSREL, delta_1 accuracy, and root mean squared error, RMSE, to quantify performance. In terms of image manipulation tasks, we demonstrated the ability to generate RGB images conditioned on depth maps, showcasing the model's effectiveness in maintaining identity and producing photorealistic results. The combination of studio and in-the-wild data allowed our model to generalize well across various practical scenarios, as confirmed by both qualitative and quantitative results.
What were the key results obtained from your experiments, particularly in terms of quantitative metrics against state-of-the-art models, and how do these results support the effectiveness of your proposed method?
In our experiments, we evaluated the performance of our model on monocular depth estimation using a dataset of 1264 images, achieving superior results compared to state-of-the-art monocular depth estimators like Marigold and Sapiens 1B. Specifically, our method outperformed these models in metrics such as absolute relative error, ABSREL, delta_1 accuracy, and root mean squared error, RMSE, demonstrating its capability to accurately capture facial shape and expression while minimizing artifacts. Qualitatively, our model produced depth maps that better aligned with the RGB images than those generated by fitting a 3D morphable model, indicating that our approach effectively learned depth correlation from the combined studio and in-the-wild training data. Additionally, the integration of the reference net was crucial, as removing it led to a failure in capturing the identity of the reference image, further supporting the importance of our architecture. Overall, these results validate the effectiveness of our joint learning framework for generating high-quality RGB and depth outputs in various applications.
What limitations have you identified in your method, particularly in terms of generalizability and computational constraints, and how might these affect the overall applicability of your approach?
The limitations identified in our method primarily revolve around generalizability and computational constraints. Firstly, our model is currently trained on depth maps derived from registered 3D geometry, which restricts its ability to predict depth maps solely for the facial skin region when presented with new RGB images. This limitation affects the model's applicability to a broader range of subjects and scenarios beyond those it was trained on. Secondly, due to modest computational resources, we face challenges in scaling our training datasets and durations to levels comparable with existing audio-driven portrait animation methods. Consequently, this constraint may hinder the model's performance and robustness, suggesting that longer training on larger datasets could significantly enhance the quality and generalizability of the generated outputs.
Based on your findings, what directions for future work do you suggest that could further enhance your method or address its current limitations?
Based on our findings, future work could focus on expanding the training datasets to include a wider variety of facial regions beyond just the skin, which would enhance the model's ability to predict depth maps for diverse features. Additionally, increasing computational resources and training times could significantly improve the model's performance, particularly in audio-driven portrait animation, allowing for more complex and higher quality outputs. Another direction could involve refining the integration of the reference net to further stabilize and enhance the generation process, potentially by exploring different architectures or training strategies. Furthermore, investigating the application of our model to other domains such as full-body animation or non-human subjects could broaden its applicability. Lastly, enhancing the model's ability to generalize from studio data to in-the-wild scenarios could be achieved by incorporating more diverse training samples and advanced domain adaptation techniques.